In this video, we're going to go over a situation that I like to refer to as when the use substitution rule is close enough. So close enough is something that takes place on a regular basis when your variables work out okay, but your constant multiples don't necessarily work out okay. So an example of that situation would be the integral of the x squared times the square root of x cubed plus 7 dx. Now, as soon as we see that we have a square root of something that's not just x, that is officially a composition of functions. So in that situation, I would say for our substitution, let's let u be equal to what's on the inside of the radical. Then, for our differential substitution, du, this would be equal to 3x squared times dx. You'll notice that in the integral we don't actually have a 3x squared dx, but we do have the variable parts, the x squared and the dx. This is a situation that I refer to as close enough. As long as the variables are working out okay, the constant multiple doesn't matter nearly as much because constant multiples can be moved inside or outside of an integral at will. So I can perform a substitution on the x squared times dx. So a little reordering will be in order. Square root of x cubed plus 7, and then we'll put the x squared times dx all together. This allows me to make a substitution. The x cubed plus 7 will become square root of u, and the x squared times dx will become du divided by 3. Now again, this would count as a constant multiple, therefore I can move it outside of the integral as a 1/3. We'll still have an integral of the square root of u, and in anticipation of the power rule, we'll express that as a 1/2 power. The 1/3 sticks around. The 1/2 power on u will get bumped up to 3/2, and then we divide by the new power. We'll also include a plus c on our result, since our integration is done. Now we can take the 1/3 times 2/3 and express that as 2/9. And for the u to the 3/2 power, we'll go ahead and substitute back. We'll refer to that as x cubed plus 7 raised to the 3/2 power, plus c. So again, I refer to this situation as close enough when we can get the variables to work out, but not necessarily the constants. Let's take a look at another example. I would like to consider the indefinite integral of the secant squared of 5 theta d theta. Now I actually see a couple different layers of compositions with this problem due to the fact that the secant is being squared and due to the fact that the input to the parentheses is 5 theta. Now with that in mind, I can think of the secant squared as being a basic form for an integration because I know that that's the derivative of the tangent function. So I'm going to say, let's let u be equal to just what's in the inside of the parentheses, 5 theta. Now theta is our independent variable in this case, so for our differential substitution, du is going to be equal to 5 times d theta. Now we don't have an extra coefficient of 5 anywhere around here other than inside the parentheses, so what I'm going to do is divide both sides by 5. That should put us in a slightly better form. So that tells me that d theta is going to be equal to du over 5. Then I'm at liberty to make a couple of substitutions here. So the secant squared of 5 theta will change into the secant squared of u, and the d theta will be substituted with du over 5. That du over 5 can be thought of as 1/5 times our integral. Now again, secant squared does have a nice basic form for an antiderivative, and that'll be the tangent of u plus a constant. Now with that in mind, now would be the time to substitute back. So this will be 1/5 times the tangent of 5 theta plus a constant. And of course, if we want to check this, we can take the derivative Derivative of the inside will give us an extra factor of 5, and it'll cancel with the 1/5, leaving us with just the secant squared of 5 theta. So that worked out pretty well. Let's try one more. The one more that I'd like to try this time is going to be the indefinite integral of the cosine of the square root of x divided by the square root of x dx. Now in this case, there are a couple different layers of where we can see that there are things going on with compositions. I would say the biggest composition that I see is the cosine of the square root of x. So what I'm going to propose is let u be equal to the square root of x. Or in anticipation of the power rule, we'll call that x to the 1/2 power. Now with that in mind, the differential substitution that we would need would be du, which will be the derivative of this. That'll be 1/2 times x to the negative 1/2 power dx. Now that would technically be 1 over 2 square roots of x times dx, which means that I can take this square root of x from the denominator and this dx at the end and include that as part of our substitution, but what we don't have handy is that extra 2. As a result, I am going to multiply both sides by that 2, and the substitution we'll make on our du will be 2 times, or excuse me, the substitution that we'll make on the 1 over the square root of x times dx will be 2 times du. So to be clear about all of the algebra that's taking place, we're expressing our integral in the following fashion. This is the cosine of the square root of x times 1 over the square root of x times dx. This will be the cosine of square root of x will become u, and then 1 over the square root of x times dx will become 2 times du. That 2 is a constant multiple and therefore can be pulled outside of the integral. Then we are free to integrate the cosine of u, treating u as our independent variable. That'll be 2 times the sine of u, plus a constant. Then of course we'll substitute back and arrive at 2 times the sine of the square root of x, plus an unknown constant.